Imagine you are strapped inside a spacecraft, violently accelerating upward through the atmosphere. The laws of physics dictate that the intense physical force pressing you down into your seat must be accounted for by the exact same universal rules that govern a person standing perfectly still. To see how physicists originally attempted to explain those rules, take a look at this three-dimensional grid. For centuries, science assumed the universe operated on a rigid, clockwork geometry, exactly like this, where parallel lines extend to infinity and never cross. In this classical model, space was a passive, empty stage. Time was entirely detached from that stage, ticking forward at a single, absolute rate for everyone, everywhere in the cosmos. This geometric model allowed early physicists to calculate the effects of gravity with incredible precision. But it created a glaring theoretical gap. It offered no physical explanation for how massive objects actually pulled on each other across millions of miles of empty void. Isaac Newton himself was unsettled by this. He could map the orbits of the planets flawlessly, but to do so, he had to accept gravity as an action at a distance, an invisible, almost magical tether yanking massive bodies together through nothingness. That accepted reality held until 1916, when Albert Einstein published a paper that completely abandoned the empty stage. He realized that a true universal theory of physics couldn't rely on mysterious tethers. To explain how gravity actually worked, he had to move past humanity's common sense understanding of geometry, proposing a structure of the universe that defies human intuition. Einstein approached the problem with a simple thought experiment. Imagine again that you are inside a windowless ship in deep space, accelerating at 9.8 meters per second squared. The floor pushes up against your feet, creating a distinct physical sensation. Now compare that to standing on the surface of the Earth. The physical downward pull you feel is exactly 9.8 meters per second squared. Because these two sensations are physically indistinguishable to the observer, Einstein deduced they must be driven by the exact same underlying mechanism. This required merging two previously distinct concepts. Space and time could no longer be treated separately. They are inextricably woven together into a single dynamic four-dimensional fabric known as spacetime. Einstein defined space as an active physical medium, a substance that reacts and moves in direct response to the matter resting inside it. Look at this representation of the space-time fabric. When a massive object, like a star or a planet, is placed within it, it physically bends and distorts the grid around it, pressing down like a bowling ball on a flexible membrane. When a smaller object travels nearby, it doesn't get pulled by an invisible tether. It simply follows the natural slopes and curves created in the fabric. What we experience as gravity is just objects falling into the spatial depressions made by heavier masses. If you find it difficult to picture three spatial dimensions physically bending around a fourth, you aren't alone. The human brain evolved to process a flat 3D world, making this geometry physically impossible to truly visualize in our heads. But the mathematics dictate a simple, reciprocal rule that governs the entire cosmos. Spacetime tells matter how to move, and matter tells spacetime how to curve. To prove this abstract math-described reality, physicists needed an ultimate test. If the fabric of space itself is physically curving, then even a massless beam of light should be forced to travel along a bent path. During a famous solar eclipse observation, the moon blocked the glare of our sun, allowing astronomers to see the stars positioned directly behind it. Their light was visibly shifted from its normal location, deflected by the massive gravitational depression the sun creates. This exact same geometric model finally explained why the planet Mercury's orbit had long-standing unexplained wobbles. The extreme curvature of space so close to the sun was skewing its path in ways classical physics couldn't account for. We see this on even larger scales with gravitational lensing. When light from distant galaxies passes around incredibly dense objects like black holes, the space is warped so intensely that we observe multiple distorted images of the exact same galaxy. These consistent observations proved that we live in a non-Euclidean universe. The classical grid-like rules of geometry don't dictate reality. Instead, we inhabit a dynamic, warped environment where parallel lines absolutely can intersect. Yet, as successful as general relativity is at describing planets and stars with smooth, continuous geometric curves, it ignores the other half of the physical world, the jagged, probabilistic behavior of subatomic particles. When physicists attempt to combine the equations of relativity with the rules of quantum mechanics, the framework explored by massive detectors like this one, the math breaks down, producing nonsensical infinities. We can usually keep these theories separate, but inside the infinitely dense singularity of a black hole, or during the very first fraction of a second of the Big Bang, objects are both incredibly massive and microscopically tiny. We need both theories to apply simultaneously, and right now, they refuse to cooperate. Einstein successfully mapped the grand, sweeping shapes of the cosmos. But bridging the gap between those massive geometric curves and the subatomic world remains the central, unfinished chapter of modern physics.